Hello friends, I welcome you all to this session on power plant engineering. So today we are going to model the reheat Rankine cycle, and where we are assuming that the turbines and pumps are behaving ideally. So let us do it. So the first point is the boiler pressure, which is nothing but 150 bar. Then the temperature at the point 1, that it means the inlet temperature of the steam is 550. Then the enthalpy can be evaluated as enthalpy based on pressure and temperature for water. So this is pressure, this is temperature. Then the entropy can be evaluated as entropy based on pressure and temperature for water. So this is pressure and this is temperature. So once this has been done, then what we can do is point 2. Now point 2, the entropy at point 2 should be same as entropy at point 1, and the pressure, the reheat pressure is given to us as is how much? 30 bar. So first let us write the reheat pressure point 2, which is nothing but this one. This pressure will be same as point number 3 pressure. So what we'll do, again we'll write this also. And okay, if I'm writing the pressure, let us write all the pressure. Point 4 should be having the condenser pressure. So this is condenser pressure. Point 5 again the condenser pressure. So this is condenser pressure, and point 6 is the boiler pressure. So it is this one. Okay, now point number 2. So the entropy at point 2 should be same as the entropy at point 1 due to reversible adiabatic or isentropic expansion. Once this is known, pressure is known, so I can find out what is the temperature at this point. So temperature based on pressure and entropy for water, this is the pressure, this is the entropy, and that's it. Now comes the enthalpy based on pressure and entropy for water. So this is pressure and this is entropy. Once this has been known, then I can come to point number 3. So point number 3 should have the same temperature as that of point number 1. It cannot go above. It can be below, but it cannot go above. So I am assuming that point number 1 and 3, they are at the same temperature. So the temperature at point number 3 should be the same as the temperature at point number 1. Okay. Once this is known, so I can evaluate the enthalpy based on pressure and temperature. So this is pressure and this is temperature. Likewise, you can also evaluate the entropy based on pressure and temperature for water. So this is pressure, this is the temperature. So then comes point number 4. Now the entropy at point 3 and 4 should be same, reversible adiabatic expansion. So here the entropy should be same as this one. Once this is known, you can evaluate all the parameters. That is temperature based on pressure and entropy for water. This is pressure, this is entropy. Then the enthalpy based on pressure and entropy for water. So this is pressure, this is entropy. Okay, point number 4 is also known to us. Then come point number 5. So this is saturated liquid, and if you want, you can also evaluate the dryness fraction at point number 4. So this is basically based on, let us say, pressure and entropy we will evaluate. So based on pressure and entropy for water, so this is the pressure, this is the entropy. Okay, it is very close to 1. Oh, great. So okay, so now point number 5. So this is saturated liquid, okay, corresponding to condenser pressure. So T sat is the temperature based on this pressure. Now comes enthalpy. So it should be enthalpy of saturated liquid, enthalpy of saturated liquid based on the pressure. Okay, now entropy will be saturated liquid based on pressure. So this is the one. Then comes point number 6. Now point number 6 and 5 should have same entropy. So this is the one. Why? Because this is reversible adiabatic expansion compression. Now comes the temperature. So temperature based on pressure and entropy for water. This is the pressure and this is the entropy. Then comes the enthalpy, that is H based on pressure and entropy, let's say. So this is the pressure and this is the entropy. Once this is known to you, now you can evaluate all the parameters which normally we do. So let us copy this here and let us, where can I do? Okay, let us do it here. So now first thing is your turbine work. So turbine work, it is H1 minus H2. So H1 minus H2, oops, what I have done, equal to H1 minus H2 and then plus H3 minus H4. So plus H3 minus H4. Okay, this is your turbine work. Then the pump work, it is equal to H6 minus H5. So where is H6? This is the H6 minus H5. Oops, sorry, minus minus H5. Now heat input, it is Q1 minus Q6. Sorry, H1 minus H6. So it is H1 minus H6 plus in reheater, that is H3 minus H2. So H3 minus H2. Okay. Now comes Q2 heat loss. It is nothing but H4 minus H5. So it is H4 minus, sorry, H4. Where is H4? This is H4 minus H5. Done. So you have your parameters. So the net work output from this cycle will be 1339 and the net heat output, net heat input should be the same as net work output, as this is a cycle close one, and the efficiency will come out as 37%. Now you can juggle with the parameters. You can see here the exit is almost on this line. We can bring it slightly more, we can bring it down. So that can be done with the help of this. If I reduce this slightly, or what I can do is, what I can do, so let's say what will be the impact if I increase this or reduce it, or will we be doing it in next lecture in more detail? Okay, so in this lecture what I have done is I have told you that how to model a Rankine cycle, and that too reheated Rankine cycle. Now you have your all the tools with you. So in the next lecture what we'll do is we will try to analyze this, or the impact of this particular reheating on the Rankine cycle. We'll also see what is the optimum value of reheat pressure and how to obtain it. Okay, in fact in the Excel itself. So in this lecture till this point only. Thank you very much for watching it.